Very high level overview, there's essentially three components that make up the storage area network. The first of them obviously is the actual disks. So the storage array or the disk enclosures where we're actually housing our physical disks, whether these be spinning platters like SAS disks or SATA disks, or whether they be the solid state disks, the SSDs. Basically any enclosure that's talking to the network that's actually housing the storage. This is going to be basically the most important component, because that's where our actual reads and writes are going to the physical storage. Then we have the storage area network switches, whether these are fiber channel switches or they could be regular Ethernet switches if we're doing FCOE. They could be IP routers, or they could just be normal layer 2 LAN switches if we're doing something like iSCSI. But it's going to be some sort of interconnect that's getting the traffic from the storage array down to the end host, which then is going to be the third component, the host bus adapter, or the HBA. So the HBA is essentially going to be like the NIC card that's talking to the storage network. In the case of FCOE, this is going to be our 10 gig converged network adapters, or CNAs, but this could also be a native fiber channel link, or it could be something like an iSCSI adapter that's doing hardware offload of the SCSI encapsulation over TCP and then over IP. Now the first, as I mentioned, first component we have here is the actual storage array. So this is where our physical disks are going to be located. Now there's different types of storage arrays. Of course, they're going to be based on the density of the disks that we can have, the type of interface that we're using to talk to the array, so whether this is fiber channel or it's a fiber channel over Ethernet. But the overall idea of this is that it's used to offer block level storage access to the servers. Now this is different from a basic fundamental point of view of what would be known as file level access. So when we compare something like network attached storage, or a NAS, versus a SAN, or the storage array, when we're talking to a network attached storage, like something that you would mount with Windows file sharing or network file system, NFS. The difference is that for the storage area network, when we actually mount the disk, the end server sees it as if it was a directly attached disk. So from Windows perspective or from Linux perspective, there's no difference from a disk that is attached via the SAN and a disk that is attached locally. So we're writing at the block level, so whatever our low level storage protocol is, then that's going to be going to the storage array. Now inside the storage array, of course, there could be different types of how the disks are configured. The main two categories we could put these into are the JBOD, which is just a bunch of disks, and then we have RAID, which is for redundancy, a redundant array of independent disks that's basically going to allow us to have fault tolerance onto the disks. Now, in our particular case this week, we're going to be using just a JBOD, which means it's essentially just a storage enclosure that has multiple physical disks in there, and then we're interfacing with it through native fiber channel. But this doesn't necessarily mean that it's not a storage array or it's not a SAN. For the high-level storage arrays like EMC, Symmetrics, or whatever your NetApp storage arrays, the main difference between them is that those larger storage arrays are obviously going to have higher density of disks, but they're also going to have multiple levels of redundancy. So physical redundancy in terms of redundant power, redundant disks, redundant I/O controllers. But from an actual networking point of view, when the server looks at the disk, it doesn't really know what type of disk it is addressing. So whether it's on a JBOD or whether it's part of some sort of RAID array in hardware, from the SAN design point of view, that's really outside of our scope. So as long as we can present the disk to the network, which we'll see is sometimes called the logical unit number, or the LUN, and then the LUN can be addressed by the initiator, which is the server. That's really all that we care about. We need to know the details of what actually happens inside of the storage array itself. Now again, as I mentioned, the storage array should not be confused with the network attached storage, the NAS, or the direct attached storage, the DAS. Where direct attached storage, this is going to be your normal local physical disks that are directly connected to your servers. Now, in a lot of environments nowadays, especially when we're dealing with big data, like how Google's index works or how Microsoft Bing search index works. A lot of these networks today are actually moving away from storage area networks and back onto directly attached storage. But from a normal enterprise point of view, typically it's more of a hassle to use direct attached storage from a management point of view, where we have to now manage potentially hundreds or thousands of 1U or 2U servers that have individual disks, and we have to do health monitoring on them. We need to do backup and recovery of them. So in cases that we're not using some big data file system like the Google file system or the open standard equivalents of them, a lot of times most enterprise networks will be moving towards using the storage area networks versus the direct attached storage. Okay, then, as I mentioned, we have the network attached storage, the NAS, which is normally your NFS or your Samba shares or SMB or your CIFS file shares. So basically anything that you mount as a network drive is not truly a storage area network. It's just that you're running a storage protocol on top of your normal IPv4 or maybe your IPv6 network in order to talk to those type of shares. Now, the storage array itself normally is going to interface with the network in one of three ways. So typically 3 different interfaces. There are a couple other ones out there like a InfiniBand that we're not really going to get into the details with. But in general, there's going to be 3 main ones that we would deal with. First and foremost is going to be fiber channel, which is the most common. So for today's fiber channel networks, most of them are either 4 gig, 8 gig, or 16 gig. There is a standard that is proposed to go beyond that, but most of the time when we're now looking at the newer arrays that are going to be doing native fiber channel over Ethernet, it makes sense to go just to FCOE and then go to 40 gig E or 100 gig E, because those are standards and those are actually introduced now. You can actually buy 100 gig E modules, as opposed to something like 20 gig fiber channel or beyond. That stuff is still in the research phase. It's not all of it has been standardized. So as I mentioned, typically fiber channel is going to be the most common. That's what we're going to be using this week. We have fiber channel attached JBODs. We're not going to be dealing with native FCOE storage, but most of the higher end arrays nowadays will have native FCOE support. Okay, the next one we have is iSCSI. So your low-end arrays or your mid-range arrays, a lot of those times they'll have normal Ethernet LAN ports that you plug into your regular layer 3, layer 4 IP, TCP network, and then you're going to be addressing this over IP. Now there are some design limitations when you're looking at iSCSI versus native fiber channel. One of them mainly being is that the IP network is not lossless automatically. So in order to run iSCSI and to make sure that my writes going to the storage array and that my reads coming back from them are not dropped, we have to implement a significant amount of queuing and QoS at layer 3 IP, as opposed to fiber channel, which natively has that built in with the buffer-to-buffer credits and the flow control we're going to talk about later. And in the case of FCOE, we have the new data center bridging standards with priority flow control and enhanced transmission selection. It's a little bit easier to implement that from a larger scale point of view versus how iSCSI is. So iSCSI is good for small, medium type deployments because it's very simple to implement. Really, you don't need any special storage knowledge. You're just taking a storage array that has an IP address, putting it on the LAN, and as long as your servers can ping that address, basically they would be able to address the logical unit number, the LUN. Okay, then lastly we have the FCOE native arrays. So these are going to have your 10 gig Ethernet ports that are running converged Ethernet. Now the storage array itself, of course, is not going to be running LAN traffic other than for management. It's going to be running the SAN traffic. So essentially we have these 10 gig links that are dedicated just for storage. So in these type of designs, this is typical where you would have some sort of large aggregation or core Ethernet switch that is attaching to the arrays, like Nexus 7K, for example. So we may have multiple 7Ks in the core of the network that have multiple F1 modules or multiple F2 modules. Then we're doing essentially a layer 2 port channel that goes to the storage array. So we have a lot of bandwidth that's going to the targets, which is going to be where our reads are going to and where our writes are going to. The next portion then is going to be the actual switches, where of course the goal of the switches is going to be to get the end servers to actually talk to the arrays. So the logic here is going to be the same as a normal Ethernet switch. Where Ethernet switches normally are going Ethernet to Ethernet, same is going to be true with fiber channel SAN switches. We're normally going fiber channel to fiber channel. There are cases, though, where we can do conversions between the protocols. We are going to take a look at that a little bit this week when we deal with iSCSI, and we look at how the MDS can take fiber channel traffic in and then convert that into IP in order to talk to an iSCSI. Actually, it would be the other way around. It would be taking iSCSI from the initiators, so taking IP packets in from your servers, then converting that into fiber channel to talk to your fiber channel storage. But most of the time, your SAN switch is going to be fiber channel to fiber channel, like an MDS 9200. It could be the larger ones, the 9500s. Most of the time, that's going to be just fiber channel to fiber channel. Now, as I mentioned a little bit before, the two terms that we use for this, the fiber channel to fiber channel switching, are the initiator and the target. So the server that is trying to access the storage resource, they are considered to be the initiator. So they're initiating the write or they're initiating the read, saying I want to put some bits onto the disk or I want to get some bits from the disk. Now then, as I mentioned as well, we can do some interoperability. So like a layer 3 IP router, where in IP I could have one link that's running Ethernet, another link that's running layer 2 frame relay or PPP or packet over SONET with HDLC, and then I could do a protocol conversion between them. So the fiber channel switches, some of them can do this as well. That's what the little I means at the end of the 9222I, means that it has IP storage capabilities. So in our case, we'll see that we can convert fiber channel to iSCSI. We can also convert fiber channel to FCIP, which is going to be for basically doing long distance tunneling of the storage traffic. And then we have fiber channel to FCOE, which is going to be what our Nexus 5K is doing. So we could be receiving fiber channel over Ethernet from the initiator, so in from the server, and then we're changing this into fiber channel in order to talk to the regular SAN switches or to talk to our directly attached fiber channel storage. Now you'll also see the term thrown around here with some of the SAN switches of directors versus switches. Now the only thing that the director means, or the term director, is basically just a big switch. So think of a Catalyst 6509 versus a 2960. So the main difference is that 6509, not only is it faster, but it has higher port density because we have line cards of 48 port GigE or more than that. But also the big issue is that we have redundancy. So with something like 6500, we have redundant power supplies, we have redundant supervisor modules, we have redundant line cards. So if one line card goes down, we can continue to forward. This is basically what they're talking about when they say a director class switch. So something like the MDS 9513 or MDS 9509, it's basically just a redundant chassis, but it's doing the same job as a normal fiber channel switch. So really, it's the same thing. It's just some of the terms you'll see here in storage networking are a little bit confusing when we're coming from the LAN-WAN world. Okay, the next component we have is the host bus adapter, or the HBA. Now the HBA is essentially the NIC card to talk to the SAN. This is what's going to go in the actual end server. So it's getting our server to talk to the switches, then the switches are getting the traffic to the storage and vice versa. So the storage array will have host bus adapters depending on what particular protocol that it's running. So if it's running fiber channel, it's going to have fiber channel HBAs. If it's running FCOE, it's going to have an Ethernet NIC card like a converged network adapter. If it's running iSCSI, it's going to have an Ethernet card that's running IP on top of it. So we generally have three different types of HBAs here then. Okay, the first is the traditional fiber channel HBA. So this can run anywhere from 1, 2, 4, 8, 16 gig. But the key is that this is going to be used just for SAN traffic, just for storage traffic. Now, when we talk about the newer designs with converged Ethernet and taking the storage traffic and the LAN traffic, so SAN and LAN, and then converging it to one link, or what's called unified wire or unified fabric, one of the advantages of doing that is that we get to remove these fiber channel HBAs from the design. Because if we're talking the scale of hundreds or thousands of servers, this is going to be a huge investment in the physical infrastructure and just the daily maintenance and the amount of power that's drawn, the amount of space, the amount of cooling for a separate fiber channel infrastructure versus the just having one unified infrastructure with the LAN. So by far, this is still the most common install base. FCOE is starting to take off, but fiber channel has been around for many, many years. So it's very common that you're going to see FC. It's more so nowadays is that we're slowly migrating towards FCOE because we now have the speed at 10 gig E or beyond that we can put both of those on the same link and then make sure that the storage traffic is not going to be dropped. Okay, we also see that there are some dedicated iSCSI HBAs or iSCSI NIC cards. So this sounds kind of strange because iSCSI is just normal IP, so why would you need a NIC card that's specific for iSCSI? And the reason is that you're doing a hardware offload of your SCSI encapsulation. Because the server is still trying to do normal SCSI reads and writes, it's just that this is now going to be encapsulated inside of IP, as opposed to be encapsulated inside of layer 2 fiber channel. So your fiber channel HBA is normally doing the hardware offload from the CPU of actually doing the encapsulation, so building your layer 2 fiber channel frame. In the case of iSCSI, we need to do the same thing, but it's now going in an IP packet. So the iSCSI HBAs, usually they come in either 1 gig or 10 gig. If you're already going to 10 gig, a lot of the times it would make more sense to go to FCOE. But then again, it depends on what is your storage array. If your storage array is only iSCSI attached, then obviously you're not going to be able to use FCOE. Okay, if it's the other way around, you can do some conversion. I could have iSCSI on the initiators and then fiber channel on the targets. But sometimes the interoperability design just becomes too complicated. So for new deployments, a lot of times it would make more sense to go to native FCOE, but for any type of small, medium business deployment, maybe iSCSI is going to be a good option because it's generally cheaper from the arrays and from these type of cards. So like the FCOE CNAs typically are maybe $1,000 or more per NIC card. So depending on what the scale of the amount of servers you have is, it can be a pretty large initial expense, the capital expense, in order to actually buy the NICs. Okay, not to mention the special cabling that's required, like your twin-ax cabling or your fiber cabling, or in the case of iSCSI, you could just run that over just your legacy copper 1 gig network, or in some cases 10 gig Ethernet also supports copper as well. Okay, so then the third variation we have there is the FCOE converged network adapters, or the CNAs. So the CNA is what we're going to be dealing with when we get to the unified computing system. So those cards that they're talking about there, the mezzanine cards that are either by Emulex or there's some specific Cisco ones. Basically what they're doing is taking the fiber channel requests in from the bus, like from the CPU saying I want to do a write to the network. Then they're converting that, what is a SCSI read and write in fiber channel, and then putting that inside of Ethernet and then sending it out the link. So we'll see that from like a physical cabling point of view, from a physical management point of view, a lot of times it's going to make more sense to go for FCOE simply based on the savings of the amount of space, the amount of power and cooling that we need to use. But there are going to be some other design considerations that we need to take into account. So these CNAs, they do a hardware offload of the FC traffic on top of Ethernet, but when we actually get into the implementation here, there are some considerations that we need to take into account. What is the particular generation of the card? So there's a difference between the first gen cards and what are now today the second and third gen cards of, are they implementing the fiber channel in an FC ASIC and the Ethernet in an Ethernet ASIC and then binding the two or bridging the two together versus combining them together in a single processor. So from a standard point of view, when we look at the FCBB5 spec for FCOE, there's a difference from the Gen 1 cards versus the Gen 2 cards. There are going to be some features that are not supported on the older cards in terms of hardware. Like, can I plug it into the Nexus 2K, or can I only plug it into the Nexus 5K, or can it go directly to the 7K? Then also from a negotiation point of view, when we're looking at the data center bridging, the DCB and the data center bridging exchange, the DCBX, how does queuing work and QoS with the first gen cards versus the second gen cards? So it is something that you need to take into account. You can't just buy any 10 gig CNA and assume it's going to work in your particular design. So next we're going to look at the specific hardware topology that we are going to be using this week. It's mainly going to be made up of 2 Nexus 5Ks, 2 MDS switches, and 2 storage arrays, or 2 JBODs, that we are then addressing from multiple different types of servers. So we're going to be having fiber channel attached servers. There's server 2 in the middle that's actually attached to all 4 switches at the same time. So it can do redundancy, like failover. If one of its links goes down, it can fail over to another switch. We then have servers 3 and 4 that are single fiber channel attached to the 5Ks. And then we have server 1 that is dual attached with 10 gig Ethernet, where that is our CNA, our converged network adapter, that is running both the LAN traffic and the SAN traffic at the same time. Now, specifically, the hardware that we're using, and you'll see the link here, you can use that right now if you want to download the topology. So I would recommend to do this as a reference for the different examples that I'm going to be going through are going to be based on this physical topology for the rest of the week. So the first switch is an MDS 9222i, which is the one that's in the hardware spec at the exam. The second one is actually a 9216i, which is pretty close to the 9222, except it runs a little bit older code revision. Now, from our functionality point of view, since this is not really CCIE storage, we don't need to go through every single possible feature of MDS with a fine-tooth comb and worry about it. We're mainly dealing with just some of the core functions of fiber channel, things like zoning, trunking, the MPIV, NPV, and the configuration between both of these versions we're going to see is fairly similar. So if you were to build this topology, you don't necessarily need 2 9222s. You could use 9216s, or you could use some of the other platforms. Really, the key here is the lowercase I at the end, which means that it does have IP storage features as well. So it means that we can take our iSCSI traffic and convert it into fiber channel, or we could take our fiber channel traffic and convert it into FCIP in order to go long distance storage over the data center interconnect. Okay, we then have the 2 Nexus 5Ks, and specifically these are the 5548 UPs, where the UP means unified port. Again, it means that we can run native fiber channel and we can run Ethernet at the same time on any of the ports. Okay, key here is that the 5548 is a fiber channel switch, but it's also an Ethernet switch. This is different from the Nexus 7K. So the 7010s right now are not in the diagram. I'm going to be showing that a little bit later when we get to FCOE. There's not a ton that you need to do on the Nexus 7K as it relates to storage. And the reason why is that it is not a fiber channel switch. So Nexus 7K currently is only native FCOE. And furthermore, it's only native FCOE on the F1 or the F2 cards. And if you're using the F2 cards, you're going to have some limitations as to the version you can run, and then the supervisors. You need SUP 2 or SUP 2E in order to run the F2 cards. We then have the actual storage arrays, the JBODs. And what is going to be significant about this, if we take a look at our diagram here, is that the JBODs are dual attached. So we have FC10, and actually that should say 2 there. FC10 and FC20. Basically, there's multiple physical ports that we have connected to the storage network. And this is going to be used for a design that's commonly called SAN A and SAN B. Now, what SAN A, SAN B is, we're going to get into this in more detail today, but essentially allows you to have redundancy in the network, that if I were to have a failure of one of these switches, let's say that MDS switch 1 goes down, I would be able to reroute my fiber channel traffic or any of my storage traffic that normally was going this direction to the storage array. I would be able to reroute it to another switch that's dual attached to those same disks. So essentially it means that I have multiple physical paths in the network that I could use in order to address the same storage. So it means that from the server point of view, ideally we don't want to have to unmount and remount the drive, especially if we're doing boot from SAN. So if you're doing boot from SAN and your OS actually lives on the storage array, then any failure of the storage is going to be catastrophic to the server. So Windows is going to crash, or Linux, or your database is going to crash if you are unable to write to or read from the disk that you're actually booting your OS off of. So that's really the key reason why the JBODs are dual attached here. We'll see that the specific ones that we're using this week do not have a built-in RAID controller. So what this means is that when they present their disks to the end hosts, now specifically each of these JBODs have 16, I believe these are SAS drives. I think they're 15,000 RPM drives. So each of them have 16 drives. Normally from a real SAN deployment, you wouldn't necessarily want to offer all 16 drives to the end host. So let's say I have a Windows server that's running Exchange, and I need somewhere to host my Exchange database. I probably wouldn't want to present all the individual drives to the server and then say to the server, okay, now you take this and make a RAID 5 set out of it, or make a RAID 0 set out of it. And the problem with that is that now it's up to the server in software in order to do the writes to the multiple disks, versus the actual storage array doing it in hardware with a hardware-attached RAID controller. And this is really what the main difference is from the JBOD versus the actual storage array. So if you're looking at something like an enterprise or data center class storage array like EMC or NetApp, you're not going to be presenting the storage to the initiator in this way. But in our case here, the ones that we're using are basically like small business or medium-size disk enclosures. That they have a good amount of disks. They have 16 drive bays each, but they're running in what's known as fiber channel arbitrated loop mode, or FCAL, which is not as efficient as running in fabric switching mode, which is what your actual enterprise class storage arrays would run as. So we'll see the design is going to be a little bit different than you would see in your practical implementation. But from the network's point of view, it's going to be the same configuration-wise when we're looking at things like zoning, things like vSANs and trunking and port channeling. It's just that we have some type of storage that's going to be addressable via the servers. Okay, then we also have the actual HBAs that we're using to talk to storage. In the case of the fiber channel ones, I'm using QLogic here. There's some single port QLogic plus the 4-port QLogic on server 2. Then for the FCOE, I have an Emulex FCOE CNA, the converged network adapter, which again is the two 10 gig links, so two 10 gig fiber channel over Ethernet or 10 gig Ethernet links that are going directly to the 5Ks. We could also have these going to fabric extenders if we had the 2232, which is the 10 gig FEX. Then we'll see once we actually get into the FCOE design, there are some limitations as to can I do virtual port channels, and can I do virtual port channel from the 5K to the FEX, from the FEX down to the end server. So all that VPC design that we spent so much time talking about previously in the Nexus class, it is now going to be coming into the storage design as well. So even though the idea of FCOE is that we have that unified fabric where LAN and SAN is going to be running on the same links, when we start to get into the details, you'll see it actually, in some cases it doesn't work that way, where we will have to split off physically Ethernet links that are going to be dedicated for our SAN traffic, and then separate physical Ethernet links that are going to be dedicated for our LAN traffic. Because there are some design problems of this SAN A, SAN B, where we're trying to do basically physical separation of the network. And if we have virtual port channels in there where we're kind of blending the definition of, when I send my traffic out, how do I know which physical device it's going to? Is it going to SAN A or SAN B? We run into some problems there that we need to address. Okay, then lastly, as I mentioned before, UCS, we're going to be discussing that later. So once we get to the UCS class, We're also going to be introducing the fabric interconnects, the FIs, into the storage network. We'll look at running those in fiber channel switching mode and in fiber channel NPV or node port virtualization mode, which is going to be really the typical design. So they can run fiber channel switching, but really you wouldn't want to do that. NPV is really made for scalability and for manageability of the storage network, and it basically takes what used to be a fiber channel switch and then changes it into a much dumber device that you don't need to worry about all the fabric service protocols. So you don't need to worry about zoning, you don't need to worry about fiber channel name service, domain ID registration. A lot of that is much more simplified when we look at running NPV versus regular switching mode. So we will talk about NPV this week. We'll look at putting the 5Ks into NPV mode and then look at the MDS running in NPIV mode, where NPIV is going to be the upstream switch, NPV is going to be the downstream switch, and then we'll see how that changes when we're running NPV for regular fiber channel and when we're running NPV for FCOE. So it's not necessarily a feature that is just for FCOE. You can run it in regular native fiber channel. So as I mentioned here, the Nexus 5K that we're using is the unified port model, the 5548 UP specifically, where there's also another model, the 5596 UP, which means that any of the ports can run as either one 10 gig E, or they could run as 1248 native fiber channel. Now, as I mentioned briefly before, one of the physical differences here is that Ethernet uses a different layer 1 framing than fiber channel does. So if you look at the FC0 spec, which is basically like their layer 1 of OSI, and you compare that to layer 1 of Ethernet, so how does Ethernet run over fiber, or how does Ethernet run over copper, like what does the 1000 base T spec say? There's different actual layer 1 framing. So it means that your optic, your SFP that you're using for your 10 gig E, is not the same optic that you would use for your 8 gig fiber channel or for your 4 gig fiber channel. So that is going to be a consideration. You cannot just plug the fiber in to the 5K and then plug it into your fiber channel HBA or your storage on the other side and assume it's going to work. It has to be a fiber channel specific optic that is using that particular speed. Now there's also some other caveats that we're going to see here, is that on the 5K, when you're dealing with the 5548, the ports need to start at the end and count down. So this means that you cannot have non-contiguous ports of fiber channel on the platform. So in the case of 5548, they're going to start at 32 and then count down from there. So I could say that ports 32, 31, 30, 29, 28, those are going to be my fiber channel ports, and then everything else 1 through 27 is going to be native Ethernet. Now when we do this, when we change the modes, we're also going to require a reboot of the module. Now depending on which particular platform you have, there's going to be a little bit difference in the behavior here. Now in the case of 5548, there's essentially 2 modules. And let's take a look at the website here while we're talking about the hardware spec for this. So let's go to cisco.com/go/nexus. And then down to the 5K, let's say compare models. And we have the 5548P, the 5548UP, and then the 5596. On the 5548, it says that you can run a fiber channel, which is here, but you need to run the expansion modules. For the 5548, natively you support up to 48 because each of the ports can be either fiber channel or Ethernet. Just depends on what you set the mode into it. But here there are 32 that are built in. Over here on the right of the switch, that's where the expansion module is that you could put other FC ports in there. Now in the 5596, if we look at the details here, and let's see if we can look at the detailed view of it. The 5596 is basically like a 5548 on the bottom, and then 3 additional modules on the top. So what this means from a fiber channel point of view is that any of these ports can run natively as Ethernet or fiber channel. So same as the 5548 UP. But the difference is that in this module, or in this switch, there's basically 4 modules. There's the module that's on the bottom, and then there's the 3 additional modules on top. And the reason that this is important is that when you're changing from Ethernet to FC, so changing to fiber channel, you need to count the ports down from each individual module. So what this means is that on the first slot here, I could say that the first 2 banks, so the first 32 ports, I'll run those as native Ethernet. Then the next bank, which is going to be from 33 up through 48, I could run these all as fiber channel. Then the next module here on the upper left, I could run that as native Ethernet. And then the next one I could run as fiber channel. Because the key is that when you're changing the port modes, you need to count down, but only on a per module basis. With the 5548, there's basically one module that's built in, which is the 1 through 32. That's why we'll see when we actually change this in our example here, if I want to reallocate a port, it means I have to save my config and reload. So from a data center design point of view, this is actually a big deal, because if you want to provision new fiber channel, it means you need to schedule a maintenance window basically to take the switch out of service. So then if I'm doing something like VPC between 2 platforms, so I have just active standby for load balancing, I would need to fail over. Once the failover is complete, then I could take the other switch out of service to reboot it, and then once it comes back, fail back. So it's not something as simple as just saying change the port to fiber channel and then you call it the end of the day. Okay, so you do need to take that into account when you are when you're looking at this. Also, from the documentation point of view, it's kind of hidden where it shows you how to do this. The config is really straightforward, though. It's only a couple commands. You say slot and then specify the module number, where in the case of the 5548, the first module is slot number 1. Then we specify what the port mode is. So port 24 to 32 or whatever I want to specify. I just need to make sure that it is at the top of the range. So if we take a look at the command line here, and let's look at one of the 5Ks. If we look at let's just look at the show run. And we should see here the section that says the slot. So it says slot 1 ports 24 to 32 are type fiber channel. So now when I look at the show interface brief, they're going to show as 2 separate divisions. So we can see here on the top, those show the native fiber channel ports. Then as we go down, this is Ethernet. So Ethernet is starting at port 1 and counting up. So it's port 1 to 23. And then fiber channel is at the top of the range, so 24 to 32. Even though it lists the fiber channel first here, they're the high port numbers, not the low port numbers. So it means that the configuration obviously is going to be different. The fiber channel syntax is different than regular Ethernet switching, but it also means that some of the verification is going to be different whether we're dealing with the native fiber channel or the regular Ethernet. Okay. Also, some basic things like if I wanted to do port channeling in fiber channel. Okay, it's the same logic as doing a port channel or an ether channel in Ethernet, but the difference is that I call this a SAN-port channel and not a regular port channel. And when we look at the show port channel usage, as we talked about in the Nexus class, it says what are the port channel numbers that I have already used, but it says it doesn't include the SAN port channels. So this means that when you're actually implementing this and maintaining the platform on a day-to-day basis, you need to keep track of what are the numbers that I've already used for my Ethernet port channels, like maybe my VPC member ports, versus the SAN port channels, because you cannot overlap them. Like if I were to go to global config here and say interface port channel 1, it says I can't do that because number 1 is already dedicated for a SAN port channel. So I need to say interface SAN port channel 1. So we'll see once we go through the syntax, a lot of the operation of fiber channel is fairly straightforward at the end of the day. It's just, for a lot of people, it's a very big jump coming from the LAN-WAN world, just trying to understand how does this correlate to what I'm used to. Like, how does the zoning correlate to what an access list does? Or how does the fiber channel name services correlate to what would be like my ARP cache or my CAM table? And it becomes kind of difficult because a lot of the terminology that's used in SAN is not standardized between the vendors. So what one vendor calls a trunk is not what someone else calls a trunk. Or what an ISL is in SAN is not the same as what ISL means in LAN. ISL in LAN means it's a Cisco proprietary trunk encapsulation. Where an ISL trunk in SAN would actually be talking about a port channel that's between multiple switches that are non-Cisco. So it gets kind of confusing as to what the terminology is. So for a lot of those in class this week, I'm assuming that's where most people are coming from, because if you're already a SAN engineer, you probably don't need to be in this class. But if you're coming from LAN/WAN world, that's where we're going to be spending a lot of time this week, is looking at the conversion between the two of them, looking at the similarities, looking at the caveats of when we do the SAN configurations, what do we need to verify, what do we need to troubleshoot, and so on and so forth. Okay, the next thing we have then is the Nexus 7K. Now, as I mentioned, the Nexus 7K is going to be used only as an Ethernet switch. So it does not support native fiber channel like the 5K does. However, it does support fiber channel over Ethernet. It does support FCOE. We're going to be talking about this later towards the end of the week, once we've already gone through all the fiber channel, once we've gone through IP storage extension, once we've gone through FCOE. This is going to be one of the last topics that we look at, because then it kind of ties everything together. Where would the 7K fit in your storage design if it's not a fiber channel switch? Now, there are some additional hardware caveats and requirements about the 7K. So first and foremost, FCOE is not supported on the M cards. So M1 or M2, those do not support FCOE. We need either F1 or F2. Now, we already know that for F2, in the current releases, they require their own VDC, but also for F2, it does have a different requirement of the supervisors and the version. So it needs 6.1.1, which is pretty much brand new as of today. Of course, in the future, the feature requirements are probably going to change. But there's also a requirement here about the virtual device contexts. So we previously saw that the VDCs, or the virtual device contexts, were used for physically separating the control plane, the management plane, and the data plane between an individual chassis. So we had the Nexus 7010, which had one supervisor, it had one M1 card, it had one F1 card. I could take that one platform and then break it down into 4 different logical switches, or 4 different VDCs. With the SOUP2E and SOUP2, if we have there's a license that allows you to go further. You can have up to 8 VDCs plus an additional management one. And this is a big design consideration here when we're talking about storage. And the reason why is that storage does need its own VDC. And in the case of using SOUP1 with the F1 modules, it means that you're now only having 3 usable VDCs, 2 if you count that you're not going to use your default for actual data traffic. If you want to use your default just for management, you have default dedicated for management, you have storage dedicated for your FCOE switching, and then that's going to leave you 2 left over for doing things like OTV or maybe Fabric Path, which again have their own requirements about what particular modules and features can be in the individual VDC. So this is going to be a special type of VDC. It's not like a user-created one, or not like the previous user-created ones that we saw up to this point. It is a storage VDC. The main idea of this is that it's like an MDS switch inside of the 7K. But again, it's not a fiber channel switch. There are no line cards currently that have actual fiber channel interfaces. The only line cards are F1 and F2 that are the 10 gig Ethernet. So we're going to come back to this in more detail later, how FCOE works on the 7Ks, and then what are the particular limitations of this particular platform. So as I mentioned there, if you want to open up the diagram as a reference for what we're going to be doing throughout the week, let me put the URL up again here. It is iane.co/SAN diagram. So this is going to be showing the physical topology that we're working with. I will be having additional logical diagrams as we're building different network topologies for vSANs, virtual SAN trunking. When we're looking at the SAN A, SAN B design, we're trying to do failover from the actual host to one vSAN versus another one. We'll have different logical topologies, but really it's going to be fairly close to what that physical network looks like. So it's not like in CCIE routing and switching per se, where you have your physical topology and it's completely unrelated to your logical topology. In the case of storage, your physical topology and logical topology, they're almost basically like on a one-to-one basis.